Okay, so let us start. As usual, some brief reminder. Last time it was a theorem, so what was that about? And that's basically the cornerstone of the whole construction. So if we have a local Martingale, with continuous trajectories, then there exists unique increasing process, which we denote this way. Again, this is a random process with continuous trajectories such that m squared minus this new one is a local Martingale again. And moreover, there is a way to construct it. It's called quadratic variation, and there is a way to construct it, you know, exactly as a quadratic variation. Just take any sequence of nested partitions and take the limit of that. Like this, the limit is in probability. Okay, so if the Martingale was a Brownian motion, then the quadratic variation is T. So that's what we know. And the theorem claims, okay, it exists for any local Martingale. And let me also add some small remark. The small remark is that I didn't say any, well, basically any word about the initial value of the Martingale. So, okay, this construction does not depend on a node. You should think that, okay, if we are given a Martingale with non-zero initial value, just add a random variable to every MT, I mean something measurable with respect to F node, and that's it. Well, morally it works. It might be some issue with integrability, so if this random variable is really bad, then for instance, so if you have say an integrable Martingale and this is not integrable, then you lose integrability, right? But if we are working in a class of local Martingales, then there is always a way, you know, to bypass this issue, choose localizing times properly. And then it was a proposition and everybody was quite tired when I tried to prove it, including myself. So what's the proposition about? That's about integrability. So the two statements are equivalent. Two statements are equivalent. The first is that this is a true Martingale and it's square integrable. And the second is that the quadratic variation is square integrable. And we are in the conditions of the theorem. So let us just spend 5 minutes checking why it works. Say from left to right. Yeah, and I forgot to write. In this case, if it happens, in this case, this m squared minus quadratic variation is also a true Martingale. So somehow what this proposition tells us, it tells us that the natural classes of martingales and finite variation processes to consider are square integrable here and just integrable there. That there is a sort of a correspondence. Okay, so how does it work? From left to right. So what should we do to check that this is finite? Okay, let us introduce some stopping times. Introduce tau n with the infimum of all t such that mm is at least n. Then just stop this process, which is a local martingale at time tau n. Note that this guy is uniformly bounded by just supremum or maximum, everything is continuous, maximum over 0t ms squared plus the second term, which is increasing and which does not exceed m. And then note that this is a random variable which is in L1. Why? Just because we know there is Dub's maximal inequality, so we need to check, okay, this is bounded, we need to check that this is integrable, and we know that this maximum, the expectation of this maximum is bounded by 4 expectations of MT by Dubs. Okay? So this variable is integrable. The expectation is finite. And because of that, we have a local martingale which is bounded by, by random variable in L1. So this is a true martingale, not only local. Okay? So, and then we can apply optional stopping. And we know that the expectation at any given time is 0. It's the same as at the origin. And okay, it means, what should I bound? I should bound this guy. It means that the expectation of the quadratic variation at time t mean tau n is the expectation of mt tau n squared, right? That's exactly what optional stopping says. And anyway, this is again the value, I mean, it's definitely less than the maximum, and the expectation of the maximum is less than the expectation of mt squared. So I can just write this way in any case. Well, and now this is independent of n, right? So I can just pass to the limit. Now. And to infinity, and what I arrive at is that the quadratic variation is finite. The expectation of the quadratic variation is finite. Yeah? By Fatou theorem, for instance. Okay, good. Other way around, that's morally in the same style. Again, introduce some stopping time. What's now our enemy? This could grow too fast on some events to be true Martingale. It can be unbounded in a very, it could be unbounded in a very weird manner, but okay, let us check it does not happen. Introduce stopping times which are infimum. The time when it exceeds n. Again, note that this now is dominated by what? By n squared plus the variation. And variation is an increasing process, so it's dominated by n squared plus the quadratic variation at time t. So again, this is integrable by our assumption because now we have a control on the quadratic variation. So this is a true Martingale. And again, just apply optional stopping, and what we see is that this expectation is the expectation of the quadratic variation, and again, this is an increasing process, so it's definitely less than the expectation of mm t, which is finite. And again, letting n to infinity, sending n to infinity, allows us to say that, okay, as n tends to infinity, then the expectation is less than that. So what I checked is that the Martingale is actually square integrable, right? I still need to check that's not it. I still need to check that this is a true Martingale. So I told you that when I discussed local Martingales is that this is not enough. I mean, it could be that the local Martingale is square integrable, but still you lose this property. Okay, what should I say here to check that it is a Martingale? Okay, well, I need a bit more space, maybe here. So what I also know is that we also know that mt tau n converges to mt as n tends to infinity almost surely. So we know two facts. First, we know the uniform bound in L2. And second, we know almost sure convergence. What I'm saying is that it's enough to claim that they converge in L1. So what I would like to say is that from this 2, we can deduce that this converges to mt in L1. Why? Okay, if you have a bound in L2, a uniform bound in L2, what you know is that if you take an event of small probability, say of probability, whatever, 1/10, then the integral of the difference of this and that over the set of probability 1/10 is bounded by L2 norm, which is finite, multiplied by 1/10 of this Cauchy-Schwarz. So what the uniform estimate in L2 allows you to say? It allows you to say that the integral of this difference over a set of small measure is uniformly small. And then, as we know, almost sure convergence. So what you say, okay, I have a set of almost full measure where these guys are close to each other, and this contributes not that much to the integral, to the expectation of the difference. And then there is an exceptional set, but on an exceptional set, I know that I cannot gain too much. Just a very standard claim. So if you have a bound in LP with P greater than Q, and you have almost sure convergence, then you have convergence in LQ. Okay, good. As we know, the convergence in L1, okay, this is a true martingale. Why? Now for any Z bounded Fs measurable, you just write the expectation of Z mt is the expectation of, is the limit of expectations of Z mt tau n. This is a true martingale, so you say, aha, this is the expectation of Z m s tau n. And now you pass to the limit other way around, so you say, okay, it's the expectation CMS. So basically, if we have a convergence in L1, then of course the Martingale property is kept, right? I mean, the Martingale property is something about expectations. So if we know that these guys are martingales and they do converge in L1, okay, we're done. And the convergence in L1 just follows from the uniform bound in L2 and almost sure convergence. Okay, so let me again repeat this comment. So now we have an impression that there is a good class of local martingales, namely those, well, not local, okay, true martingales, namely those which are square summable. Okay, then yet another remark, maybe here. Bracket of two local martingales. The idea is that this behaves like a quadratic form in M, right? So there is a standard way to extend it to a bilinear form. Okay? So definition, if given two local martingales, you just denote by Mn T what it should be. So for m plus minus n, we can measure the quadratic variation, and then we just extend it to a bilinear form. There is a bunch of simple properties. What are those? Just not to forget something stupid. First, this is a finite variation process. Okay, this is increasing, that is increasing. The difference of increasing functions is a finite variation function. This is a finite variation process. Then, what else should I say? Okay, this is a, yeah. This is a local martingale. The proof is basically trivial, so you rewrite everything using this identity, which is called polarization identity, and you deduce this property from the fact that m plus n squared minus the quadratic variation is a martingale, and the same holds for m minus n. So this is a local martingale. In particular, we know that these two conditions define can be used to define this bracket, right? Uniquely defined by these conditions, because there are no non-trivial local martingales of finite variation. Then B, you could by A1 and A2. And then B, you can wonder when this is a true martingale, right? So you apply Cauchy-Schwarz basically if you know that both are square integrable, then this is a true martingale. And yet another property, let me save some space and write it here. Sorry for this. These terms can be constructed as a quadratic variation using any sequence of nested partitions. Obviously, you can translate these to the bracket. N by the increment of n. And the limit is in probability. Similarly to the limit here. Again, this is trivial algebra. So you know this statement for m plus n, you know this statement for m minus n. Okay, you do this polarization in each term of the sum. Good. Are there any questions so far? If no, yet another comment here. So example. I mean, what is there? yet another notion, and the most important example in a sense. So another notion is the two martingales are called orthogonal. If let me write it other way around. So if this bracket is 0 for any t. So in a sense, you should think in the following way. Okay, we have something, a sort of a Hilbert space. And this is a sort of a scalar product. So that's the notion of orthogonality. And example, the most important example, is given by two independent Brownian motions. the calculation is trivial, right? So if we have, we should define them on the same sigma algebra. This is not a big issue. You just take two filtrations, on the same filtration, sorry. You just take two filtrations and construct basically union of them. So then B plus B prime is a Brownian motion with rescaled time, right? So that's normal variables. So basically what you do is rescaling time. And so you know that basically, you know that whatever sign you choose, this is 2t. Okay, so that's an example. Okay, good. Now we are ready to construct the integral with respect to a square summable Martingale. Integration with respect to Martingale. Maybe should I delete something? No. So what is the idea? Let us try to remember what happened last week. I mean, from where we started the whole story. So it was a sort of a motivation for the construction of an integral against with respect to dB, right? So we just considered some sums, something like that. And let us try to develop a similar motivation here first. Imagine that what I would like to do, I would like to define this for some class of processes HS. That's my goal. The first question is what are the basic processes for which this definition is somehow straightforward, for which I'm sure what the answer should be. So, as usual in the integration theory, the basic processes, the elementary processes are step functions. Okay. Let HS be of the following form. This is a finite sum of some. It depends on omega. It is a random process. I'm not going to write omega, but okay, it's always behind. And here is indicator of that. And what are constant C's? They again random variables. So this is a step function. It's deterministic in S. These times are deterministic too. And these are random and measurable with respect to f tj minus 1. So the picture, we fix some partition, well, sometimes, not partition even, just sometimes. And then we consider all the step functions with this additional measurability assumption. So I should know what is the value of the first stairs just from the very beginning. So this is determined by the information up to time t1, and so on and so forth. Okay. And for these processes, I just define this process h dot m, which is another notation for that. Just two notations. I mean, two, well, yeah. I just define it, okay, in the most trivial way. How should I integrate the step function? Immediately see I should write the sum over all j, cj, m, t, mean tj minus mt, tj minus 1. Let us think for a minute about this step by step. So what happens if t is very small? If t is here, then all the terms except the first one are zeros, trivially, right? Because here we have mt and here we have mt too. So what we have is just c naught, c1. There, okay, c1, which is measurable with respect to f naught, multiplied by the increment mt minus mt naught, which is 0, and I didn't say it. Where? Is 0. So I just integrate the step function. Then when t is somewhere here, what I have is a contribution of the first segment plus, c2 by mt minus mt1, and so on and so forth. So that's trivial definition. Okay, what do we know about the result? So first, I didn't say it, M is always a continuous process. So for me, all the Martingales, well, they continuous. So first, what is the correct order? It still has continuous trajectories. Well, this is trivial because what you do, you integrate with respect to some continuous function. I mean, this is trivial from the fact that M is continuous. Well, and C. Well, again, later it might be some issue with integrability. So let me assume also that C's are bounded. Right here, it's not of importance. But okay, let me assume that these random variables are uniformly bounded. Okay, it has continuous trajectories. Second is the Martingale. Why? Okay, just think about this step by step. So imagine you have, say, S here and T, whatever, somewhere there. So what we would like to check is that for any Z bound at Fs measurable, we need to prove that the expectation of Mt minus Ms Z is 0, right? That's what we need to check for a Martingale property. What is this difference? This difference is just the sum of increments here multiplied by some c, here multiplied by some c, and here multiplied by some c. What I'm saying is that the Martingale property of M tells me that this last increment is independent of, well, okay, it's not independent, but if this increment is multiplied by something measurable with respect to the previous sigma algebra, the expectation is 0. Okay? So what I'm saying is that here, okay, there is a sum of increments. Well, a bit ugly notation, but here. It's clear what goes on. At least I hope it's clear. So basically there, this is just it's either mt minus mt yod or mt yod minus mt is 1 or mt yod minus ms. And it's just the increment of m over either this part of the last step or this step or the part of the first step. And then you just say, okay, of course it's 0 by the Martingale property. And then the most important remark is C. Which is again absolutely similar to the remark I made last week in the Brownian motion setup. So let us just compute the expectation of this guy squared. What's that? Okay, we square this sum. As usual, there are many cross terms, but the expectation of all the cross terms are zeros because of the Martingale property. It's clear just because we have the increment here, the increment somewhere else, and everything except this last increment is measurable with respect to f on the left hand of this increment. So that's the Martingale property. So all the cross terms cancel out. What I have is first this way. Okay. In fact, I can push it slightly more and say replace the square of the difference by the difference of squares. Why? This is the standard trick, just because if I subtract this from that, then what I have is again the increment over this segment multiplied by well, I'm not going to write it, just an exercise. Check that this is again a Martingale property, which allows us to do this. And then, what I'm saying is that, in fact, now I can replace mt squared by the quadratic variation. Why? Again, just imagine we subtract this from that. What we have is C j squared by m squared minus mm at time tj minus m squared minus mm time tj minus 1. So this is the Martingale property for m t squared minus m t. Is it clear? Okay, good. But now I just interpret it as the integral over 0 t. Yeah, well, there is a sort of a mess here. So what I'm doing, I compute it at the very, very end. So I compute it at time t, when t is tp, right? I mean, so I'm not taking care of this minima. So let us just compute at the very end. Or maybe, okay, no, maybe even better is to take care of that and to write min t everywhere, so it still works. And then I just say, okay, I can rewrite the last sum purely deterministically as this integral. Right? Just a computation. So it says, and this is exactly the same as what we did with the Brownian motion. The key new ingredient is that we have this process now for any Martingale. So we need here something to replace m squared. And we just have constructed it. Okay. Now there is a standard plan to define this integral, the standard recipe to define this integral for a wide class of processes. So we know what to do with step functions. We have a sort of an identity in L2. Just use it and define this guy by this isometry. So what we need is a space on the one side, a sort of a Hilbert space, for instance, on the one side, another space on the other side. We need to check that they are complete. Okay, not a big issue. Maybe we need to check that these processes form a dense subset. But when we did, I mean, if it's done, then okay, the construction of integrals with respect to L2 Martingales is finished. Okay, let us make a break and then do all that. So let us continue. So here is the bottom line of the first half. I have this isometry, and now what I need to do is basically to introduce appropriate spaces. So now we introduce spaces. So let it be denoted this way. Throughout this paragraph, I think that I'm given a Martingale MT, which is square integrable. Okay, so it's fixed. This, by definition, is the set of processes HT on 0t, progressive. This is some measurability condition. Okay, it's going to be discussed actually slightly afterwards, such that the expectation of what of integral 0 t h t squared d mt is finite. Some mess with the notation, but basically this is what you see here. Okay, here t capital is replaced, t small is now replaced by t capital, and s is replaced by t. And then let me denote it A2 star m. This is going to be Hilbert space, and this is going to be the norm in this space. So this I'm going to denote by H A2 Tm. Just a small comment. It might happen that on some events the quadratic variation does not grow for a while. The extreme case is just a martingale, which vanishes, which is always 0. Then, well, as usual, we should factorize by the set of H's with 0 norms. So this is not a norm, but a semi-norm. It's technical and I hope clear. And if we work on the whole half line, then okay, just consider in a sense the intersection, the limit of all these spaces. So this is the set of HT such that H A2 0 Tm for any t capital. And okay, this is not a Hilbert space, but this is still a norm. I mean, yes, a norm space, not a norm space. What should I say? I should say, yes, something like that. That I declare the norm in this space to be something cooked up from these norms. Well, this is fairly standard construction. Something like that. Convergence in L2 star is nothing but the convergence in any of what is T, 2 to K for instance, or just K, is the convergence in all of the spaces on finite intervals. Topology in this space is just given by the topologies of truncations. Okay, good. So this is the space for the right-hand side here. And now I need some space for the target. And for the target, it would be M. What's that? This is the set of all martingales with square integrable martingales with continuous trajectories. With continuous trajectories. Such that the expectation mt squared well, a sort of a mess, because this m is now not the m which is fixed throughout this section, but I hope it's still clear. Just have in mind remark B. What I should get as a result, this process h dot m, should be a martingale with a continuous trajectories, right? So it should belong to this space eventually. And again, this is I declare to be the norm in 2, 0 t, And in a similar fashion, I denote M2 star, for instance. This is 0t, sorry. This is the limit of all them. T with the norm defined in the same way. Not going to rewrite it. I mean, that's exactly the same expression. Again, the only thing which is important here is that the convergence, the topology, the convergence in the space is given by convergences in all the finite segments, on all the finite segments. Okay, good. And now, what should I prove about the spaces? It should be a map from here to there, which I hope to define by an isometry. So first, probably I should prove that this is a complete space, and so maybe here it's not absolutely necessary, but what I should prove definitely is that my simple processes are dense in this space. But in a way, I still need, well, okay, it's easy to check its complete Hilbert space, and processes are dense. So the first important message is that here there is nothing deep. Actually, this is just an L2 space on some, with respect to some sigma field. So that's what I'm going to explain. So denote by P the following sigma algebra. So this is all the sets from what? From tensor with B0t. So this is the sigma algebra A calligraphic is the sigma algebra in omega, such that for any t A cap 0t is in Ft tensor B0t. Right now, this is some formal definition. Okay, it's not hard to check this is indeed a sigma algebra. Well, trivial exercise. The message is that the process is progressive. So here we have a space of progressive processes, and you could have an impression that, okay, this is, well, some tricky measurability condition, but actually this is exactly, so claim is that the process is progressive, 0t. If and only if this mapping omega t to ht omega is measurable with respect to this sigma field. Well, I should confess that I'm not always good with such statements. I mean, you just check this in silence. There is absolutely nothing there, so I'm not going to check it. On the blackboard, you see what's the definition. So the definition of the progressive process is that any restriction on the subinterval should be measurable with respect to this sigma algebra. So this is exactly what's written here. The message which is understandable is that, okay, the notion of, of being progressive is just measurability with respect to some sigma algebra. Okay, exercise. This is basically one line, but my experience is that it does not help to write it on the blackboard, because either you see it's trivial or you still don't understand, and then you need to check it in silence. At least personally, I'm always in either the first case or the second. So, okay, and then you can view this as just an L2 condition with respect to some measure. So then note that L20Tm is nothing but the standard L2 space, the L2 space on what? On omega S0T with respect to this sigma algebra, and the measure, what is the measure? So the measure basically is written there. So this is D. Okay, to measure some set, I just take the expectation of the integral of the indicator function of this set, which also depends on omega T dMMT. So just think this way. For any sample, okay, this is not formally very correct, but imagine that we have a right to consider this for any sample. For any omega, we have a given measure, which is dMMT. Okay, and then you glue the measure on the tensor product from these sheets. Okay. Because of this remark, there is nothing, nothing deep to think about this space. There's just the L2 space with respect to some sigma field and some measure. That's it. So the question is why simple processes are dense. We continue here. So why simple processes are dense? Okay, as this is a Hilbert space, what we actually should check is that there is nothing orthogonal to all the simple processes. Let some H be orthogonal to in this L2 to all simple processes. And denote and let whatever this is H. Okay, let xt be the primitive of this H with respect to the quadratic variation. Nope. No, yeah, okay, that's fine. So what I'm saying, okay, I have some h from here, and I just denote its primitive. It's a convergent integral because of Cauchy-Schwarz. I know that h, it converges, it is well defined almost surely because I know that the expectation, if I put an absolute value, the absolute value here, that the expectation is bounded by the expectation in L2. Note, well defined, almost sure. And then just write the following. So yeah, that's a problem. Maybe I still can try to conclude here. So now take any, it's simple, but there is a sort of trick inside. So take any z bounded fs measurable. And then use an orthogonality condition of this h and what? And okay, let me try to write it maybe in some other color to be more visible. So let us write the orthogonality condition. Say h t by put it this way, z by the indicator of st I'm lost with indices. Okay, let it be h u z st d m u. Maybe it was. Okay, here you can put t capital or t small, it doesn't matter. So what I consider is a very simple step process. This is 0 everywhere except one segment, st. And on this segment st, it's given by z. And z is fs measurable. Okay, so here is my simple process to which I apply this orthogonality. Okay? So what I know is that it's 0. Okay? Then I can say the following. So I can just say, this is the integral over the segment s t small, right? Everything else just does not participate. And because of that, I can rewrite it the following way. So this is the expectation of what? Of z. And now I should integrate hu, from s to t, hu d quadratic variation. So at the end of the day, I would like to write, I have introduced here xt, so I would like to write xt minus xs. Hopefully let's just let me reformulate this in another way. Let me consider very simple, the simplest step process. There's just one interval and some variable. And let me write this orthogonality condition which I have. It turns out that this orthogonality condition can be reformulated in terms, this is immediate, can be reformulated in terms of this integral process of this primitive xt in this way. Okay? So maybe I did it in a bit unlogical way, so it's better to start here and then say, okay, let me just define xt this way. Then what do I know about xt? So first I know this is a Martingale because this is exactly what this condition means, right? Second, I know this is a finite variation process. Why? Just because this is constructed as an integral over some finite variation process. And such an operation keeps this property for process to be of finite variation. So I know this is a finite variation. And I also know this is a Martingale. Well, okay, this is a contradiction. The only possible case is when it vanishes identically. So what I have eventually is that it vanishes identically, and then this is exactly what allows me to conclude that the norm of H in this sense is U. Okay. So the only non-tautological message here is that this orthogonality condition immediately gives you a Martingale property for some variation process. And then you conclude by the proposition we had last time. Okay? So I pretend this is done, the first proposition. Are there any questions? Okay, good. Then let us think about the other side. So now we have a space to start from. And let us think about the target space. Again, the claim is that this M2 is a complete So I don't pay much attention to the spaces to star and to star. It's somehow trivial. So if you have a convergence, for instance, in each of these guys, then you have, by definition, the convergence here, vice versa. So why this is a complete Hilbert space? There is something to prove here. So let us take Cauchy sequence. So how to prove that the space is complete? Obviously, we have a scalar product where here it is. So we have a scalar product in this set. This is the norm, and the scalar product is given by the bracket discussed before the break. The only question is the completeness. Here is what we need to check. Okay, so what should we do? We should consider a Cauchy sequence and prove it has a unit. This is Cauchy has a limit, it's enough actually to find a subsequence that converges, right? So if inside of any Cauchy sequence you can find a convergent subsequence, you are done, because then you know that the whole sequence converges. Okay. Find MK such that MK converges to M infinity in this space. And convergence is also in the topology of this space. Okay. So again, well, as usual with Martingales, we take advantage of the loop's maximal inequality. So note that maximum over the 0 T capital and S MTM minus MTM squared expectation somewhere by Dub's inequality is bounded by the expectation squared with some constant, and this is nothing but the norm in our space, just by definition, right? I hope it's still here. This is the norm. So this is a Cauchy sequence. We know this guy is decay. In particular, we can find MK such that the expectation of this maximum from MK to MK plus 1 is as small as we wish. Okay, in particular, let it decay as exponentially. So you just wait until the norms in your Cauchy sequence, the norms of differences is less than 1, then wait until they are all less than 1/2, then less than 1/4, etc. Okay, good. And now there is a trivial remark. So what I would like to say is that basically from this estimate I know that the series composed from such differences converges over C. So let me write it in a more formal way. So if I take the expectation of maximum plus 1, right, I can bound it, each of the expectations I can bound by inside 2 norm. Write it this way. Right? So what I'm saying is that the expectation of a random variable is less than the expectation of the square. And there's decay exponentially, so this definition. Fine. So almost surely this sum is finite, and almost surely we have a limit. B for the convergence to some process, and denoted by MT. This case as to infinity, uniformly in C so okay, what happened here? I just said I had some control of the values at the right end, but I have the very powerful loops inequality, and because of that I can extract a subsequence which converges as you know, as continuous functions. I'll be sure. And now what I would like to say is that this MT should be in the space. That's my goal. I mean, this should be the limit. I mean, which I need, which existence I need to prove. Well, it's more or less straightforward, so we know. First, we know that MT is an adapted process. Remark, because this is a limit of adaptive processes. So I know that MTM is a T measure, and it's continuous. So the notion to be adaptive and the notion to be progressive is the same notion. Then we know A2 integrability. Why? Because again, this is Fatou. This is the Fatou lemma. So we know that MT squared cannot jump. It cannot be, because this is an almost sure limit of MTN, so it cannot be less than expectation. So it can be greater than the expectation. The expectations like that. Again, this. So what Fatou's lemma tells us is that when you pass to the pointwise limit, the integral might drop, but cannot jump. Okay, so this is finite. Why? Because these guys are bounded by so this is square integrable. This is adapted, and we should also check that this is Martingale. Okay. Again, what we need to check, we need to check that this expectation is that expectation for any z fs measurable. And this is exactly the check I already made during the first half. I mean, we have the control of A2 norm. We have almost sure convergence. It means that they converge they converge in L1, and that's exactly what we need to justify this. So we have this M is indeed in our space. And the convergence is again trivial, as we know that by definition the expectation of this again by phi2 the limit of another index L, say. Basically it means, as we know, the sequence is Cauchy. Tends to 0 as both tends to infinity. We know well, the only slightly non-trivial part is here, but this is very, very standard for Martingales. So the idea is always the same. If you have a control on the right end, then you have a uniform control over all t's by 2s, and then you extract subsequences. Okay, good. So now we have two spaces, and we can just define our integral. So definition when MT okay, B MT star define the mapping H HM which acts from A2 CM to again M2 M2 star by isometry. Starting this. The isometry itself is already lost, so it was somewhere later. Okay, that's nice. Still, there is a question if we really needed this Martingale to be a true Martingale in N2, not just a local Martingale. So maybe we'll discuss this a bit later, but not more details. The answer is, well, okay, let's discuss it later. Just to make some comment, note that if it was not square integrable, then you cannot start with simple processes. Because what you need to know that, I mean, for this isometry, that you have a rate constants. Right? And so if you would like to start with step functions, then you need to be able to integrate constants. And to integrate constants, what do we need to know? We basically need to know that the expectation of M is finite. So there is something for this condition. It can be then extended. So I'm not going to discuss it right now. The next step in the program is to say okay, I have defined it in a rather formal way, but still, if HT is a continuous process, in L2M as continuous trajectories, then this definition agrees with the natural approach just by Riemann sums or something like that. Then for any sequence of nested partitions, vanishing, then this sums minus 1 and converge to what? To the integral we have constructed. And the convergence is in probability. And B you consider squares, then again in probability converges to the integral with respect to the goodness direction. Well, this is not for today. We start next time with the proof of this fact. This is not very hard again. Just to give you sort of a perspective. Okay, it justifies that still for continuous processes, everything is nice. Instead of this isometry, one could just approach everything by Riemann sums. Okay, then what do we have? We know how to integrate with respect to finite variation processes. We know how to integrate with respect to Martingales. Well, square summable, but more general, in fact. And then, what is the natural idea? The natural idea is to introduce a class of processes which is called semi-Martingales, given by formal sums. So you take whatever finite variation process you wish, you take whatever Martingale you wish, you just sum them. Okay, this is some class of processes. You know how to integrate with respect to them. And then the natural question to ask, if I now have, say, semi-Martingale and I take a function of this semi-Martingale, if I still have a semi-Martingale or not. So for instance, think about bt. If I square bt, then remember we had this additional term, I mean the integral bdb is b squared plus t. So I could rewrite it the other way around. B squared is integral bdb minus t. So bdb is a Martingale, t is a bounded variation process, oh, that's nice. B squared is in this class. This is a very general fact. This is what's called in the calculus. That's what we will do next time. I mean, the very general fact is that if you now play with finite variation processes and martingales simultaneously, just with sums of them, all the natural operations you can imagine keep you in this class. So this is the class I told you about. I have a dream. I had a dream about, well, to have a class of processes such that integral x dy does not leave this class. Here it is. And we are pretty close to complete this program. Okay, that's it for today.